Okay, where do we start? So, welcome. It's a pleasure to be back here, recording down. You can see the area is going through a bit of a regeneration. It's probably going up the sexiness axis on the Mark scale. Right, so I've been commissioned to talk about the use of sequence data into modeling applied to flu studies. So the first question you may ask yourself is why? Why are we obsessed with sequences? Why do we want to use them to start with? So I think there are two obvious reasons why we want to do this. The first one clearly is that sequence data is becoming increasingly available, and this is illustrated here on the left-hand side. So this is a graph showing the number of full genome sequences that are generated over time. So there's a year here. This comes from the Craig Institute, and you can see that the number of flu genome sequences that are ready for you to exploit is experiencing a massive boom. So clearly, this is a very attractive tool. But in correct to this, there's also the increased evidence that these genomes, molecular data, actually are embedded with a wealth of information that it would be a shame not to exploit. Again, as an example here, I'm showing how just by looking at gene sequences from flu samples in New York State, you can kind of infer the kind of population dynamics, the changes in population size, as indicated here using a kind of Bayesian and CMC framework, and you can reconstruct the kind of changes in population size that correspond to the flu seasonality. So this is just one example out of many. But just to show that there is an archived memory in these sequences that we can exploit and that can help us maybe devising better public health messages or interventions. So admittedly, sequence data is widely used in the field of flu research. Okay, I've indicated kind of four broad themes. Clearly, novel strain identification is thriving. So here, this shows how the history of the H1N1 strain that was responsible for the 2009 epidemic. So the history, the recombinant history was unraveled using genome data. You can also, there's a lot of studies focusing on the molecular adaptation, which is clearly important for a viral pathogen. Then, reconstructing, broadly speaking, migration patterns and epidemic histories for virus strains is also something that you will find, in the literature. And then another aspect, which in my opinion is probably overlooked, but yields a bit of a potential, is contact tracing using sequence data. So contact tracing is done through the traditional route. However, although this is done for other pathogens, as far as I know, I don't think that this is a well-developed field in the context of flu, and we'll come back to this in a minute. So clearly, the use and the usefulness of flu sequence data depends on the scope of your study and the type of model you want to build, which is not my field of expertise. However, I think that there's several leads here that we can keep in mind. So clearly, some people are interested in modeling intra-host dynamics, and sequence data is very useful for this because flu is a rapidly evolving pathogen, so you can see in near real-time evolution going on, and you can put this into the context of a particular viral infection. But I suppose that most people are interested at the population level, and there's also several aspects like routine surveillance, where what we call real-time phylogenetics is a very fashionable topic. Although concretely, I don't think it has been lifted off the ground yet, despite very good attempts and probably promising ones like Next Flu framework, which was developed by Neher and Bedford. You can also probably, so that could help you looking at strain replacement, antigenic shift, and all this kind of information that may be relevant, in a public health context. Clearly, outbreak control, trying to make predictions, is a very important field, and I'm sure that's what keeps most of you busy. Or intervention planning, this is public health after all, and maybe, the use of sequence data could help inform models to make better estimations of incidents and to make better decisions. So, as far as I can see it, really the focus of this particular talk, lies at the interface between three different areas that are very often found, paired 2 by 2, but very rarely, all together. And these are phylogenetics, so sequence analysis, Modeling, mathematical modeling, whatever definition you want to give that term, and then clearly, as Mark mentioned, the kind of impact this may have on public health, and so studies designed to actually inform decision making. So we would like right here, and I think that it's fair to say that at the present stage, the studies that cover these three areas and fit right here may not be that numerous. So I'll give you a few examples to see what I mean. Feel free to contradict me. So we're going through like 3 or 4 examples where you'll see, sequence data has been coupled to either modeling or, public health work, but maybe not, encompassing the 3 aspects. So the first one here is this rather interesting work done by Trevor Bedford here about the global circulation of seasonal influenza viruses. So this is mainly a phylogenetic work, so heavy exploitation of viral sequences. However, this is also coupled to modeling to try to infer epidemiological trends. So the idea here is to try to understand whether the kind of global migration patterns of different strains over the time, from past epidemics were similar or comparable, and what could be the drivers of this. So this is shown here, for instance. This is an example for H3N2. Where the kind of epidemic was reconstructed using sequence data, and so this is shown as a phylogenetic tree here, which is dated, so the authors have estimated the time a particular strain will spend in a particular geographical location, okay, and use this to estimate migration patterns. But so, as I said, they also basically used, various parameters that are extracted from this phylogenes to inform models to try to estimate, like, attack rates, so infections, amongst children, and also migration rates. So they used a battery of models and different parameters. I can't really get into the details here, but this is really to illustrate how information derived from genetic data here, phylogenetic tree, basically, can be used to parameterize, a model. So in this case, we would fit, I think, right here in the sense that, sequence data and modeling are used and are very tightly intertwined. However, I think the kind of, the ability of this work to impact on public health decisions is maybe limited. I hope I'm not too harsh by saying this. This is not a criticism of the quality of this work, which is really high, obviously. But since this is, the focus of this work, I thought I would mention this. So this is an example where we have, a closer link between sequence data and, public health interventions here. And so this is a work of Christoph Fraser, who was done in 2009, right at the beginning of the, H1N1 epidemic again. And here, so this is, very interesting in the sense that, they went through the traditional kind of surveillance data, try to infer things, and in fact, this work was used to to help monitoring the start of this epidemic. But what is interesting is that some kind of epidemic parameters, such as basic reproductive numbers whatsoever, were estimated in parallel using traditional methods, for want of a better word, and phylogenetic data again, because there are nowadays ways of estimating these parameters just using sequence data. But here, I dare say that the kind of the modeling part is probably not the strength of this study. However, the public health impact was huge. Another example where you can see we're getting closer to the center, ever so slowly, is work by Neha et al. Very recently, which is basically presenting a novel framework to try to predict, what the next fashion in flu will be. So this is basically based on the Malthusian or even Darwinian concept that the fitter you are and the more offspring you will generate, as illustrated by, say, Brad Pitt and Angelina Jolie. And this will be reflected by the topology and the shape of your tree, because the more offspring you have and the more branching pattern you will see. So by identifying regions in a tree that seems to have a higher than expected level of branching and nodes, so you could maybe predict you could infer the fitness of the strains in that particular zone, and then identify potential ancestors of the next season strains. So again, I don't have time to go into the details here, but so they came up with what they call the local branch index, which is basically a matrix that allows you to identify, as I said, parts of the tree where viruses may have a higher fitness. And they tested this and reckon that their prediction, the predictive value of their framework worked pretty well in the majority of the cases. Sorry for the very precise indications here. So my point here being that this is really clearly a phylogenetic work that has a huge public health potential because it has a predictive element here. And but again, this is not strictly speaking a dynamic model, even if there's a fair level of statistical modeling on here, and some evolutionary processes are modeled within the framework presented by this work. Now let's go on to another zone here, which is where hardcore modeling meets public health, and this is some work published by Mark, which presents basically a complex model, at least for me, that incorporates source from for various origins, like surveillance data, serological data, contact tracing, everything you can have. I think there's 6 different types of information which are all incorporated into this model, and that was used to calculate the impact of different vaccine strategies, right? And so some results are indicated here. So the point here that I want to make is that maybe virus sequence data could help informing even further this, and either complementing or adding new information into the modeling, and then the kind of scenario testing that is presenting here. So now, when you want to incorporate sequence data into epidemiological work, there are some kind of questions that you may think sequence data will help answering, right? And so I've listed a few here that I drew from a review here. So the kind of questions that you most likely find in work that incorporates sequence data is is there an outbreak? What strain is responsible for an outbreak, for instance? Where or when was the origin of that particular outbreak of epidemic? Can we calculate epidemic parameters just based on sequence data only? What is driving transmission, or what are the transmission chains like? So clearly, some of these questions are not clearly relevant to to modeling, but all the others, I think, have can benefit from incorporating sequence data once again. So let's look at them one by one. So. What strain is responsible for the outbreak? I don't have a slide for this because clearly, this is more a question of, genotyping your data, and so there's not much modeling involved in here either. Oh yeah, something I forgot to say is that I think one of the key challenge is a strong word, of this particular approach is to try to determine whether it's really worth it to invest into sequence data and to incorporate this into your framework. And whether the value and the information you draw from the sequences is either complementary to the information you get using traditional inference, or if it's only confirmatory, right? Does it add something else, or does it allow you to actually confirm what you have? So can we calculate epidemic parameters? So the answer is yes. Now, we're quite lucky to live in an age where, all this phylogenetic method and, hypothesis testing based on sequence data is quite advanced. There's a wealth of tools, and they're getting increasingly sophisticated. And so indeed, there's kind of frameworks have been developed that allow you to estimate things that I know you epidemiologists deal with on a daily basis, like basic predicted numbers, force of infection and things like this. So this is an example, again, done on flu, where just by using, virus sequence data, were sampled reconstruct phylogenies, and using, a particular inference system, you can estimate, growth rates. What do I have here? So date of emergence of a particular outbreak or, of epidemic, and Arnold. And here on the right-hand side, what I wanted to show you is how actually there is a correspondence between some of these metrics and estimates you get from sequence data. Like in black here, you've got the relative genetic diversity of the viral population over time, and in the dashed line shows the reported cases over the same period of time. And you can see that there is a correspondence, if not a perfect overlap. Now, another question you may want to ask yourself. I've lost track of the time. Please let me if I'm getting over. Yeah? Okay, really? Okay. So, what is driving an outbreak? So, what is driving an outbreak? Well, so there's many ways to answer this question, and clearly, the easy way is just to ask people who are infected and just, do your magic. However, you can also draw this information from phylogenies, and this is shown here, done by Lemay et al. Not last year now, 2 years ago now. Where, again, they reconstructed the phylogeny of various strains of, H3N2, globally, and reconstructed the tree, and then basically estimated the time of the strain, so this particular lineage was spent in a particular geographical location. And so the color indicates, the countries or, geographical regions here. And then by doing so, and putting this in context and adding information from airlines and whatsoever, so kind of from behavioral data, they were able to estimate the contribution, so the predictive value of a particular indicator to the time, to migration rates and to the time a particular strain will stay in a given country, given the connectivity, the passenger flow in airlines, which are all indicated here. And then you can see that some aspects, okay, so behavioral aspects seems to be linked with the migration rates more than others. Like passenger flow here is an obvious one. Okay, so now I'd like to come back to transmission chains, which, as I said, I don't think is really well developed in the world of flu. There must be a reason. I come from an HIV background where it's actually quite interesting and important because this is an information that you don't get to start with. People don't know when they're infected, they don't know who infected them, they don't know many things. However, with flu, the context might be different, but I think there is still, value in maybe, strengthening and incorporating this into flu studies. So the principle is very simple. You've got individuals that, are infected, I'll give you 10 points. You can derive sequence data from the virus they're infected with, reconstruct the phylogeny, and based on the genetic similarity, you can group people together. You can identify people who are infected by viruses that are near identical, if not identical. But you can also exclude from your transmission chain people infected with viruses that are, clearly, more distantly related to your group, right? So that's how you establish your transmission chain. So you can do this just based on phylogenetic only, by observing and determining part of the tree that correspond to, that have features that you would expect from a discrete transmission chain. But you can go beyond that and use more sophisticated methods, like the package outbreaker here, that takes into account genetic data as well as other type of epidemiological information to reconstruct transmission tree. Okay, and probably in the most robust way. So as I said, so this is something we're exploring here, and so this is, I wouldn't even call this a result now, at least preliminary results, where we've kind of reanalyzing the data from 2009 again, seems to be the most studied epidemic ever. And so, try to establish a number of introductions into the UK and then establish a discrete transmission chain and then characterize them, as indicated here on the right-hand side, where you can see the reconstruction of one of the clusters, because it seems like this strain was introduced at least 7 times in the country. And you can determine basically the most likely location of the virus into a discrete period of time. This is a dated tree, and the scale here indicates the proportion of a year, so so the scale is about 2x. Now, what I wanted to basically, the kind of take-home message I want to leave you with is here. I've decided to leave aside, all the technical aspects of incorporating sequence data, the cost, the time it takes, the complexity of some frameworks that are required, the quality of the sampling whatsoever. However, I think there is a strong potentiality for an enhanced public health message if you incorporate sequence data into your kind of modeling approach, right? And this at several levels. Okay, you can extract information from phylogenies that would help you inform your models. Okay, and some parameters. Again, because some inference methods, and are redundant with other inference methods that don't use sequence data, you can confirm estimate calculations. However, I dare say that comparative studies are yet warranted. I haven't seen yet some kind of work dedicated to the comparisons of the quality of estimates you get using different approaches. And then, as I said, I think also, I wouldn't say the future of this study lies in reconstruct transmission chains, but this is probably something that needs to be looked in more detail, in the close future. And finally, I think also there's another potential here for genetic studies, which is to maybe try to be more inference and improve some calculations like incidence just by looking at the topology of a tree and infer what could missing links be, which is something which is done again in other pathogens like HIV. Right. So to come back to our little Venn diagram here, I may or may not have convinced you that the kind of the crossroad here is not very well populated, and again we are at the stage where both of these fields are expanding rather independently. So there's more sequence data, there are better tools to analyze it. I think the same can be said about modeling and and probably public health strategies. However, the kind of overlap remains the same, and I think this is what we need to increase. Right, just to probably have a better arsenal and just to develop better public health messages. Thank you for your attention, and I'm happy to address any questions.
We have 5 minutes for questions. Is there any question that was clear?
Maria Zambon, Public Health England. Thank you for a wonderful talk. That was really inspirational, I hope, for all of the folk who are thinking about how to apply modelling to sequence data. My question was, what thinking has there been amongst the kind of modelling fraternity about how we might use the absolutely wonderful data we have in the United Kingdom on our community infection from community surveillance linked to whole genome sequencing, because we have a very active program where our surveillance has, our virological surveillance is now almost completely whole genome sequencing on the genetic side. And what we really need to do is to think about how to use the data that we're generating on the sequencing side, but link it to the actual detailed, rich epidemiological community surveillance. And I haven't sort of heard any of that yet.
Right, me neither. So the answer is I'm not sure I have an answer for you because I'm not quite sure how this can be done, and this is in fact the focus of what we're doing together. Now, I dare say this is a bit of a conundrum, because if you think about it, let's talk about sequence data, look at phylogenetics and then surveillance in one way. I think these are two fields that look in opposite ways, right? The phylogenetics, clearly you look into the past. Okay, and so what you do is reconstruct past events and try to draw information from this. When you surveillance or public health, you look toward the future. You want to predict, you want to be reactive, you want to respond to a threat whatsoever. So it's very difficult to reconcile two fields that in fact by nature are quite opposed, and that's probably why they're not sequence data is not more present into surveillance structure. So to answer your question, I don't really know how this can be done in practice, but I know for a fact that many people are looking into this, and we may not have the answer yet. Another problem with sequence data is the time it takes to generate them, right? And so by the time you have a complete set of sequence that you can exploit, right, you may have, if not missed the boat, but you may have missed an opportunity to act quickly and just to have a very very efficient surveillance structure or response. Does that make sense? Yeah.
Yeah, just to comment on that, I couldn't agree more. From what I've seen with Outbreaker, especially when it comes to flu mutates quite fast, but the genome is small. So overall, you don't have, on average, between one case to the next on the transmission chain, on average, you don't even expect one mutation. You'll have to wait a few generations of infections to see one mutation. So genetic information is going to be useful to reconstruct the past evolutionary history, et cetera, but when it comes to knowing who infects whom and understanding how the transmissions happen, we really need to be able to incorporate all the information we have. And the epi information is probably going to do most of the job there. The the genetic data is going to be a plus, but we need to use contact tracing data if we have them, and any other location, timing of infections, etc., etc.
Here.
I think if I can add something as well, this question of mean and drivers as well. I mean, I think for kind of a sexy model, you have a kind of a thing which I've done by, for example, you've seen all these nice colorful graph, next flu, etc., which I think is much more promising if you want to kind of develop the knowledge or something. And if you're looking at more public health questions, there's already existing methods which are working that you might want to develop. And I think incorporating the genetic, as for all the reasons that Stéphane mentioned, is quite difficult. So if you have to answer relatively quickly public health questions, spending 1 year, 2 years of developing the new tools which are not really there, you cannot afford it. And I mean, I would ask a question. I mean, you know well PhD, and how many positions is there funded to do modeling with genetic sequences? None of them. And the reason is because if you're doing immunization and you want you will find transmission modelers which is don't know anything about genetics. If you want to use genetic to I don't know, inform with the strain circulating, you're going to find a bioinformatician which knows that, but who doesn't have the kind of time or knowledge to do transmission models. So I think there's a question as well of means. If you put money, now grants will give money for like advanced knowledge and all this nice fancy thing, but I think funders will not put money for to develop models which somehow are dealt with other way, kind of not too bad. You see what I mean? So I mean, I think we're all conscious, and I think Stéphane showed it very well, that there might be potential for more information, for complementing things, but also I think in public health we have already tools in modeling which do not really use genetic models, genetic in models. I'm not sure if it's anybody has anything to add to this. Or I mean, yeah. Sorry.
I mean, excuse me. So a lot of the work that you've shown so far is obviously based on hemagglutinin sequences.
Yes.
Could you comment on how much extra information we could get from whole genome sequencing?
How much, sorry?
Extra information we could get from whole genome sequences.
From whole genome sequences?
Yes.
So these are whole genome sequences?
I mean, not limited to hemagglutinin.
No, sorry, I misunderstood you. So no, most of the work I've shown is actually based on full genome sequences.
I see.
Yes.
Okay.
So you get optimal information because there's nothing left, right? So no, I think nowadays, really, we've reached an age where, you know, whole genome is becoming the standard, especially for flu. Right?
And the whole genomes do actually add a lot of information from.
Well, it has extra information, okay, because of the nature, the fragmented nature of the genome. You know, it allows you to address specific questions, especially into immunology. You know, I don't know why you would do that. And so clearly, you know, migration patterns as well. You know, maybe you know, you have more information using full genomes because the different fragments may have different histories. Okay, then they come from different places. So, and you know, we could discuss this extensively, but and also, you know, because of the mutational nature of these RNA genomes, clearly, you know, you never know where the genetic markers that would be useful will be placed, right? Although clearly, if they're driven by selection, you know where to look at. Yeah.
I'd like to comment on that last question. I think the surveillance is now delivering whole genome sequencing at a rate and in a timely fashion. We're not actually able to use the information that we're generating, i.e. we only analyse a very small proportion of it, which is entirely to do with hemagglutinin and vaccine strain match. I think there's a lot of potential for much deeper mining of data as it comes off. So I think there's an untapped potential, but whether or not that's really going to deliver public health gain is tricky. It'll provide biological insights, but not necessarily public health gain. Doesn't mean we shouldn't do it. I think we should figure out how to make use of information in a much more rapid way. I think last season we put out something like 300 to 400 whole genome sequences based on UK, and I think we've already put this season into publicly available databases probably close to 100. So my point is that the whole surveillance is ramping up for delivery of genetic data. It's how we use the information and how we mine that information. So it's a challenge for all of the modelling folk to think about this, because I think there are some insights to come from that.
That's true. In fact, we went from an age of data deprivation, where there was very little data around, to an age of data kind of obesity, where there's too much to handle. And so that actually makes, because the kind of the technology for the analytical tools is just not following the speed. It's not up to speed. And so now we're having actually tractability problems. But that's a different story.
Okay, well, thanks a lot,
Thank you.
Stéphane. And I think we can go to the next talk.